So, hello, my name is Selim Zoorob. I'm a fourth year physics major at UCR. This project is my capstone project for honors. I've been part of honors for 2 years now, and this is a project we're working on for I've been working on it extensively for 2 years as well. Even though I'm seen as and I'm part of physics, I've been working, it's a biomedical engineering project. So I had to work with the bioengineering department, and I worked with Dr. Rinant Liu, who helped me a lot uh, to develop this project. So my project is about a medical ventilator add-on splitter, and I'll be going over some background information for introducing what I've been researching. So the main project was inspired by an article I read back in 2020, where basically hospitals in New York were so impacted that they had to split a medical ventilator into two patients. So they connected tubes and they made it in a way that two patients would share one medical ventilator, and which was an inefficient way of solving this problem of shortage of medical ventilators. So then why would they do this? Why is the medical ventilator so important? Well, it's a breathing machine, and it's used if a medical condition makes it hard to breathe or get enough oxygen into the blood. What's important about the medical ventilator is that it prevents respiratory failures. There are two types of medical ventilators, the non-invasive and the invasive ones. As you can see, the invasive ones are have a tube that goes through the trachea, while the non-invasive ventilators have only like a mask system to it. And my project would evolve around non-invasive ventilation, as I'll be explaining. So here's the setup for a traditional medical ventilator in a hospital. So the main idea is that the ventilator pushes warm, moist air into the patient, and there's like an airflow, and it goes back out as exhaled air. There's a constant flow of air going back and forth, and it helps the patient breathe, basically. Here's the minimum requirements for medical ventilators to be efficient. And the main idea is what we'll be focusing on this project is the tidal volume, which is the amount of air that's moving out in and out the lungs in each respiratory cycle, which is between 200 and 800 milliliters. It depends on the state of the patient, and it's determined by the medical professional. The PEEP, which is a very important phenomenon that happens when you're connected to a medical ventilator, which I'll be explaining down the road. The plateau pressure, which is a pressure threshold that is achieved, and it's very important to prevent lung collapsing. I'll be also explaining that. And the fraction of inspired oxygen, which is basically the percentage of oxygen that's coming, that you're inhaling whenever you're connected to a medical ventilator, which could be between 30 and 100%, and it depends on the patient, and it depends on the cases. Each case varies. So the project is around solving this question. So what if we could create a device that would allow medical ventilators to support more than one patient at once? So instead of one patient per medical ventilator, let's say we can connect 4 patients into one medical ventilator in case of a shortage. And that's what I tried to answer. And there were many previous attempts in the before I came into this research field. One of them was Johns Hopkins. They tried developing this 3D printed ventilator splitter. As you can see here, it's split in two for 2 patients. but they didn't keep going with the project mainly because of three reasons, which is the cross-contamination between patients. So, each patient has its own set of viruses and bacteria and can be transmitted through the air while breathing. So that was an issue. It was cross-contamination, lack of airflow regulation. You couldn't regulate the airflow because each patient has different needs. So the air that comes from the medical ventilator is different for each patient. It needs to be different because each one is different. And low oxygen levels. Well, the low oxygen level is mainly due because it wasn't regulated properly. So 2 years of research has led me to develop a solution that could solve all these problems, and the solution would be a practical one, as it would use all the material available in a hospital setting, or if it's not available, it's 3D printable on the most basic of 3D printers. The idea started with a sketch. The sketch was, as you can see here, it's a splitter. The air comes in here and it splits into, in this case, six outputs. It would allow many patients to use a single medical ventilator. As you can see here, the key designs is that I used a spherical design for optimal equal distribution of airflow and pressure across the outputs. And I focused on making the outputs on the second part of the hemisphere and equidistant from each other for optimization. Where I thought about where would I attach it? Well, it would be attached here from the intake and the output of the machine. So it would intercept these positions in the machine. And what was it sketched into a 3D design that designed on SolidWorks 2020. I decided to go with 4 outputs instead of 6 to maintain structural integrity of the material and to avoid making the system more complex, because 6 patients way more harder to regulate than 4 patients. What was a 3D printed, what was a 3D design? Turned into a 3D printed design using ABS, and I use ABS because it can endure temperatures ranging from -20 to 80 degrees Celsius and safe for humans. And as you can see here, that's the part I 3D printed at home. So now, okay, so we have the splitter, we have the main idea, we've 3D printed it. Now, how do we does this solve the cross-contamination issue, the airflow issue, and the O2 issues? Well, no, that's why we had to develop, we had to find another solution to that, because we found a way to split the air. Now we have to solve those issues, which is the cross-contamination, airflow, and O2 levels. And one part of the solution is the PEEP valve. So many patients come into the hospital with stiffened lungs due to many issues, many diseases that cause that. So it's found that in medical ventilators, we experience PEEP, which is a phenomenon, which is a positive and expiratory pressure, which means that when you exhale, usually like when you breathe normally outside of a medical ventilator, your air pressure inside your lungs is equal to the air pressure outside outside, which is the atmosphere. But within a machine, if you were to do this, it's not possible because the machine doesn't have like a set pressure. So your lung would be at a high risk of collapsing. So what happens is that this PEEP valve can be used to make sure to maintain a positive pressure within your lungs so that your lungs won't collapse when they're weak. And the PEEP valve is revolutionary in a way that it can maintain a positive pressure, and it can also increase the oxygen saturation intake, and it also prevents collapsing. We can also regulate the PEEP valve, which is very, very important when it comes to regulating a patient's needs. So I wanted to show how the PEEP valve is regulated so we can volume control the PEEP valve. As you can see here, the amount of the flow is regulated by volume control. I mean, how much flow can go in at once. So the flow is constant. So as you can see, the flow is constant and it's regulated. And the pressure, as you can see here, it builds up gradually and then it plateaus and it goes down. But you can see here, the PEEP valve prevents it from dropping below a threshold. And this this type of phenomena where the PEEP valve regulates the pressure is also seen when you pressure control it as well. You can volume control and pressure control it. And the pressure control, as you can see, the pressure is constant as it reaches a threshold, and the flow goes down as the volume goes up inside the lungs. And you can see the PEEP valve won't allow the pressure inside the lungs to go below a certain level, below a certain threshold, which is very important. Now, this PEEP valve is connected to an apparatus, and this apparatus seems very complex, but it's very important as it basically treats and focuses on cleaning the air that's coming in and out of the patient using the double HEPA filter. Each HEPA filter, as I'll explain later on, can filter up to 99% of incoming and outgoing particles. And it's connected using 3D printed add-ons, and there's a self-inflating bag in case a patient needs more airflow coming into their lungs. As you can see here, the double filter manual ventilation system is revolutionary in a way that it can collect 99% of virus particles per HEPA filter, and we put 2 just in case. Now, these HEPA, the system itself can be assembled using material within the hospital setting. So everything here, from the PEEP valve to the HEPA filter to the self-inflating bag, can be found within a hospital setting. And the connectors are 3D printable using the most basic of 3D printers and using ABS, which is a commonly used filament when 3D printing. So everything here, the base idea of the solution is that it's feasible and it's makeable in case of an emergency situation. And this is the final setup. This is what it should look like in case we need to hook up 4 patients into one medical ventilator. As you can see, this medical ventilator, this is the 4-way splitter I designed, and each patient has its own double filter system, and to regulate the O2 saturation levels, the airflow, and to make sure that the air is filtered. Now, here are the results. So what's the difference between having 4 patients on one medical ventilator compared to 1 patient per medical ventilator? Well, the main difference, as you can see, is the O2 saturation per patient is 55 to 65% compared to ideally 95 to 97%, which is usually addressed whenever a patient is hooked up to the medical ventilator. As you can see, the flow isn't a big issue when it comes to having 4 patients instead of 1, because the flow will always bounce between 40 and 60 as all patients breathe at a different rate. And the patient can be regulated at 55 liters per minute, RPM is liters per minute. So there are different levels of priorities when it comes to ranking patients. So it depends on each medical institution, each hospital has its own rules when it comes to ethics, but it basically comes down to having P1, which is high priority, P2 patients, which is intermediate, and P3, which is not needed, and P4, which is not suitable. Well, in that case, the 4 patients per medical ventilator is aimed at P3 patients that might not need, but just in case they need it, it's there, and there's a shortage of medical ventilators, or even P2, but in the most extreme situations. Well, the 1 patient per medical ventilator is aimed at obviously P1, P2, and P3 patients. There's a question of ethics in terms of this solution can only be effective if used properly. So it's only effective if there is a shortage. It shouldn't be used as a way to so basically the medical ventilator is designed to be used individually, but it's preferred to be used that way. But if we need a solution to face the shortage of medical ventilators, that's where my solution comes in. And obviously, the hospital and any medical institution will act based on certain ethics. And whatever the institution decides will obviously depend, and it will be for the a best case scenario for the patient and for the group of patients in that certain situation. I wanted to acknowledge Dr. Richard Cardullo, the President of Honors, and Mrs. Maria Jones, my honors advisor, for supporting me during this capstone journey, and Dr. Hinan Liu, who's my faculty mentor, and she has helped me a lot during this project. These are my references. Thank you.
All right.